Welcome back to ch205. In this video, I'll be talking about numerical differentiation and integration. This is chapter 4 of our textbook. So if you remember from before, or maybe high school, the derivative is defined by taking the limit of the function at, let's say, x plus a small increment, delta x, and then minus f of x divided by the increment. So if you take this limit when delta x goes to 0, then this will lead to the derivative of f with respect to x. So this is taking the limit when delta x is positive, right? So x is actually tending to 0 from the right side of x, from the numbers bigger than x. So that's why we think of delta x to be a positive number. We can write this limit when delta x is negative, and that is right here. So the derivative of f with respect to x can still be written as taking the limit of fx minus fx minus delta x. So if you compare equation 4.4 here and the first equation we looked at, you see the difference when delta x is positive or negative. The negative delta x actually in the second equation shows up in this negative sign right here. So both actually would be giving us the derivative of f with respect to x at point x. Okay, so let's go back to the first definition. So this is now, if delta x doesn't go to 0 and is a small number, okay, if you don't take the limit and just assume that df dx is equal to this would be an approximation. Okay, so approximation comes in when there is no limit. We just write the derivative as the difference between f of x plus delta x and f of x divided by delta x. Okay, if you don't take the limit, that will be an approximation. Every approximation comes with an error. So in this case, we want to look at how much the error is, which we call it e delta x. And to understand the e delta x, we expand f of x plus delta x using Taylor series. So here is a Taylor series of f of x plus delta x, which is equal to the function at x plus, so this is by definition, this is the Taylor series by definition, plus del x times the derivative of f, which is f prime, plus delta x squared divided by 2 factorial f double prime of x, plus delta x to the third power divided by 3 factorial times the third derivative of f with respect to x, and so forth. Okay, so we're going to construct the right hand side here and see what is left over, which we call it error later on. So to construct the right hand side, if I look at equation 4.2 here, then I can subtract fx from both sides and then divide by del x. So I can reconstruct these parentheses. Okay, and that's what I did here. This is fx plus delta x. I subtract fx from both sides of this equality and then divide by del x. So on the right side, what I'm left over with is it's going to be f prime of x, right? Because when you divide by delta x, this becomes f prime of x. This one goes away. This one becomes delta x over 2 factorial. This one becomes delta x squared over 3 factorial, and so forth, right? So then I move f prime of x, or I subtract f prime of x from both sides, and what I have down the road is f prime of x, which is this term, is equal to this minus that divided by del x, and then minus this term divided by del x, minus this term divided by del x, minus this term divided by del x, and so forth, right? So if I just truncate this up to the third piece here, up to here, then I'm left over with minus del x over 2 divided by, del x divided by 2 times f double prime of x. Okay. So what I did was I truncated this series up to here, then subtract fx from both sides, then divide by del x, right? Okay, and then I subtract del x over 2 factorial times f prime of x from both sides again. So that is where I subtracted. And then if I compare this with the first definition of the df dx, or approximation of df dx, I see that the first piece, right, the first piece is identical to this piece. And then the second piece, which I introduce as the error, is going to be this. So this is on the order of del x. Because the power of del x is 1, we say the error, which is this, now it's going to be this term, is on the order or is on the scale of del x. And because the power is 1, we call it this is first order approximation. So this equation that you see here, well, up to here, okay, if I use this definition for the derivative of f, this is called first order approximation. And the reason is because the error is on the order of first order, and that is because the power of delta x in the error term is 1. So the power of del x is 1, we call it first order approximation. Okay, so we can do the same thing. Instead of having fx plus delta x, we can do fx minus delta x. And the only difference is the odd powers of delta x now become negative. So negative delta x to the third power, and so forth. The even power are still positive. We do the same thing. Now this time, I subtract fx minus delta x from both sides. And then what I'm left over with is on the right side, you see fx minus delta x. Then we divide by del x. And then you see that this is going to be f prime of x, right? I move it to the left side, so it becomes positive, and that's what it is. And then if I truncate it up to here, the error is going to be same thing. It's going to be delta x over 2 factorial times f double prime of x. So the error is exactly the same as this. The only thing is the sign here was negative. Now here's going to be so here the error is going to be positive. That's the only difference. But there's another difference between this definition of the derivative, which is fx minus x minus delta x, and this definition of fx plus delta x minus fx. So we're going to talk about this difference later on. But for now, we know that there are two ways to calculate the derivative of f with respect to x. Okay? This is again first order approximation, because if you calculate the error, we see that the error is on the order of delta x. Well, when we divide by del x, then this becomes actually del x. The power is reduced to 1. And so mathematically, we define that error as O delta x, which means the error here is on the order of, so O stands for order, is on the order of delta x, or we call it first order approximation. Okay? We can do similar analysis to calculate second order approximation for the first derivative. So let's look at that. Now this time, if I calculate f of x plus delta x and minus f of x minus delta x, and do the Taylor series as before on each term, we can do the Taylor series on each term and then add them up, we get a series like this. Now if I divide through by 2 del x, you see that I get f prime of x here, and this is going to be del x squared over 3 factorial, which is 6. Okay? So now if I want to calculate f prime of x, I can subtract from both sides of this del x squared divided by 6 times the third derivative of f, and then I can just only have f prime of x on the right side, and the left side now becomes this term. Okay, so if I look at the equation up to here, then this would be the approximation for the first derivative, and this is going to be the error term now. And you see that the error term now is in the order of del x squared. So this is in contrast to what we saw before. Before was the error was on the order of del x. Now here is the order of is in the order of del x squared. So this is called second order approximation because the power of del x is 2 in the error term. Okay? So this is the third definition of derivative with respect to x. Now I'm getting x plus del x minus x minus del x divided by 2 del x. Compare it to this one, which is x minus del x. And then compare it to the one we saw before, which was x plus del x minus x. So 3 definitions so far. There's actually a table later on in this chapter that we can look at 3 different definitions and compare them more quickly. All right, so let me actually go back to this table before I continue. So here's a table of calculating the first derivative. So we saw this definition before. Now, instead of x plus del x, we're going to use x subindex I plus 1. So imagine I have my x-axis right here, and I divide this x-axis to many intervals. At every interval, let's say the beginning of the interval, I call x as xi, the next one is xi plus 1, and so forth. So I have like many x values along the x-axis with the interval of, let's say, delta x. And the difference between xi and xi plus 1 is delta x. By the way, these are subindices. Okay? The function at point xi is called f of I, or f sub I. The function at x sub I plus 1 is called f sub I plus 1. So by this definition, I can rewrite my f prime, which is the first derivative of I, of x at point xi. Okay, it's going to be, so this is now f of x plus del x, and this is fx. Now by this definition, we can write this as f of xi plus 1, or f sub I plus 1, minus fi, so that's going to be the difference between this blue line and this blue line, right? So that's what the difference is in the numerator, and in the denominator I have this, the difference between the two x values, two successive x values. And this is, you can think of this actually the slope of this black line, right? Because f sub I plus 1 right here minus fi would be the difference between these two blue lines. It should be something around this line up to here. And I'm going to divide this by xi plus 1 minus xi, which is this length. You basically get the slope of this line in this triangle, right? And the slope of this line is approximately equal to the tangent to this red curve, which is exactly the derivative of f at point xi. So we define the derivative as roughly the slope of this secant line, right? We saw this before. So this is called forward approximation. It's forward because if you want to calculate the derivative at point xi, you look at a point ahead of you, which is xi plus 1, and then you use the function value at that point to construct the limit or the derivative. So sitting at point xi is, if you sit at point xi to calculate the derivative, you need to know the function at the point ahead of you, which is f of xi plus 1. And that is called forward difference. We have similar definition, but for backward difference. That means to calculate the derivative at point xi, okay, you look back at point xi minus 1 and calculate the slope. So in this case, the slope is going to be f sub I minus f sub I minus 1, which is right here, and divide by the difference between the two x values, which is del x. So sitting at point xi and looking at I minus 1 gives you the backward difference. So compared to the forward difference, where we're sitting at point xi and we look ahead, we look at xi plus 1. So this is called forward difference. This is called backward difference approximation to calculate the first derivative f prime. Okay, so thanks all for watching. Stay tuned for the next section on calculating the derivative of function numerically.